K1, K3. So this is a robot and it's moving. So this is more like a train, and the moment this thing has got more than one task, it's now a robot. So from that, I want to determine natural frequency of a system that is stationary. Is that so? So the robot, what we need to know is to know how you can determine the actuator. The most important thing that a robot has got an actuator. A robot has got a controller.
Wants to see.
Okay.
Yes.
A robot has got a controller. A robot has got an actuator. A robot has got a sensor. So all those things you need to design them from scratch because you are doing robotics. So the most important thing is you have to calculate from scratch how can you determine the actuator or the power of the system. In engineering, me, I'm a mechanical engineer. I started 2004 to 2008. I did mechanical engineering here. I also went to National Oil Company of Zimbabwe. I worked as a GT. Then after 2010, I came back to UZ to do masters in manufacturing systems and operations management. After the masters, I quickly went to University of Johannesburg, where I did my PhD in robotics and artificial intelligence. I now went back to do medical physics. I was now going into the route of medicine. That's why you see my office change from engineering to medicine. So I'm now more into the robots for the health sector and AI. I also have got another master's in data science. So I'm a professor of artificial intelligence and robotics, mostly. So this one is the basic equation for power. Power is equal to T omega. You know this equation? If you don't know, please let me know, especially the guys from computer science. If you want to know the power of any system, it's equal to torque multiplied by the natural frequency or the frequency of the system. So here, we want to determine the frequency of this system. So the system will be given like this, determine the mode shape and the frequency, 25 marks. So once you have something like this, you can calculate the frequency. Do you think you can do that? Yes, you are saying you are Nasha. Munashe, are you able to determine the frequency of that system? Do you know what you do?
No.
Do you think you can try? Who want to try? How to get frequency of that system? So the most important thing is we use what we call D'Alembert equation. You did Lagrange? You did Lagrange equation in simulation. I was told by Kapil that you did Lagrange. So now that you have done so, we know that our M, this is our M1. This is mass. We know from Newton's laws, F is equal to MA, right? You remember that? You remember? Sheila, you remember when you say force is equal to mass times acceleration. So the mass times acceleration is equal to the force. So here we have got a mass 1. If we multiply by the acceleration, this one is moving distance x1, this one is moving distance x2, this one is moving distance x3. So those are some distances that this thing can move. So once it moves like that, we know simply that it can actually, so how can you get a force with a mass here? So basically you have to differentiate this twice to get a velocity, right? If you differentiate once, it's a velocity. This one is displacement. You remember? If you differentiate it, it becomes velocity. If you differentiate twice, it becomes acceleration. Acceleration is just the 2x by dt squared. You remember? Is there anyone who is stuck? Just let me know so that I don't move whilst you don't know. The idea is after all this, you are now able to determine the power of how much do I need to buy for an actuator to place on this robot. We defined the robot last time and we now all know what's a robot. So this one is, we have what we call Newtonian mechanics. Unfortunately, I will do these things in Russian. We have to write exams in the next 3 weeks. Yeah? So we have to do, so this one here, M1 X1 dot plus. This one, we also have a force here. Do you know what is called Hooke's law? Do you know it? You still remember that, Kapil? Where we were multiplying K1 by our displacement, we have a force. So the total force here is this plus this one is equal to the force that is here. You get that? So something that is going this direction is equal to that. So if we say that one plus K1 X1 is equals to this one. K2, this one, x2 minus x1. Do you know this? This is displacement. Are we there? Is there anyone lost? If there's anyone lost, let me know. We are saying displacement here. This is the rate of change of displacement, x2 minus x1. So the force that is here is equal to, when we are pulling this, imagine of a train that is moving. So this one is moving, this one equals to this plus this. This one will go back first when this one is pulling it forward to go forward, right? So once you have something like that, you have your equation. So from this you can simplify your equation, right? Can we simplify this equation? We call this D'Alembert equation, and our final equation will be equal to m1 x1 dot dot plus k1 plus k2 x1 minus k2 x1 should be equal to 0, right? k1 k2 x2, right? k2 x2 m1 x1 plus k1 plus k2 plus x1 minus k2. This one is supposed to equation 1. Is there anyone who is lost here? Anyone lost? Sheila, are you lost? Let me know if you are lost, so that I know where to start again. If you are moving together, then I know you are there. Are we there? Doctor, are you there? Are you lost? If you are lost, let me know. We are saying our mass 1 multiplied by the velocity multiplied by acceleration on 1 plus the k1 x1, the Hooke's law. Those are the only forces that are acting on that robot, on that system. Should be equal to that system. So what we do is we have talked about degrees of freedom, right? The degrees of freedom for this, remember when we used to do introduction for this is degree of freedom 1, this is degree of freedom 2, this is degree of freedom 3. So the degree of freedom for this system is 3, right? So we are going to have 3 natural frequencies from that system. So that basically means this one will need its own actuator, this one will need its own actuator, this one will need its own actuator. You get that? Yes.
You start again, Prof.
Okay, where should I start?
In determining the degrees of
Okay, degrees of freedom is number of independent coordinates on a system. Something that determines that this is that. In medicine, we say the number of systems in a human being is 11, right? So that basically means there are 11 totally different systems that make up the human body. Those things are totally independent. They work on their own. The reproductive work on its own, the respiratory on its own. So 11, human being has got 11 degrees of freedom. I don't know if I'm right, Doctor. That in terms of the system that we have 11. Right? So the degrees of freedom, the number of independent coordinates that make up a system. This is a simple pendulum that we normally use in high school. We are moving this ball, and this ball is moving with an inextensible string. Remember that? The experiment that we used to do Form 3, Form 4. So when you are pushing it, the string is assumed constant. It's not going to change its length. The degree of freedom is 1. You get it? Right? Can I move on to this? Yes.
Could I ask what are the SI units for each of those terms? Like when we're using mass times acceleration, is that giving us newtons?
This is kilogram.
Okay.
Alright? So this one is kilogram meter per second squared. This is a force. Right? This one is also Newton per meter. You remember? Then this one is a meter. Then it becomes a meter. So we are adding Newton and a Newton. You get that? Kilogram meter per second squared is equals to Newton. Force. So we are adding force together. Right? So this is what we have. So this is second equation. Anyone lost on this one? I need to move on to DH parameters very fast. And I think I should move on from this. These are the simple things we are starting with. But I can see that it's stuck.
What there is like, I would want to see the rationale for having, you see the force on the mass, M1, and the force on the spring, which is the spring 1, when you add the 2, you are saying it's like actually the force that would define
Total force.
the total force of the
Total
system.
force. So total force.
Ignoring K3 there and M3.
We are not ignoring them. We are only here. We said we are on the first degree of freedom. I have done equation 1. When I am coming to equation 2, what is, so you just do this. You close this, you now focus on this.
Okay.
Because we said we have 3 degrees of freedom. So we have mass 1, mass 2, mass 3. So for this one, we're only focusing on mass 1, right? On the first degree of freedom, so that we get the natural frequency of this system, right? Are we together here? Can I move on to the second one? You can just write the second one on your own, so that I just move on and see if you understand. Let me know if you understand. Do you know how to do it, Munashi? Do you know how to do it? Or you are lost? You are lost. So the second one is you draw a free body diagram like this. It's M1, M2, X2, dot, dot. Then this one is going this direction. This one is going this direction. Then you take this one. We are here. So this becomes K2, X2 minus X1. So you have this one in the same direction with this one. Then this one you have K3, X3 minus X2. So this is the free body diagram for the second equation. You get it? So it becomes M2 X2 dot dot plus K2 open bracket X2 minus X1 equals to K3 X3 minus X2. You get that one? Do you get it now, Nash? Yes. Can you do the third one? Okay. Quickly do that one, then you do the third one. Okay, are we together? Can you do the third one? Bokang, you want to do the third one? Just say the equation for the third one. Yeah, so the third one is just this one. M3, X3, dot, dot, then it's going this direction. It's actually the smallest because this side, it has got a 0, this one. You see that? It doesn't have anything there. So it's actually 0. So it's actually this plus this is equals to 0. You get it? So the final equation that we have is M1, then the second one is M2, X2 dot dot minus K2X1, K2X1 plus K2 plus K3, X2 minus K3, X3 equals to 0. Equation number 2, M3, X3 dot dot, right, minus K3 X2, right, plus K3 X3. X3 should be equal to 0. Equation 3. So these are the final equation that we have. Once we have this equation, we can put them in a matrix so that it's easier for us to solve them, right? So can I wrap this? I'm done, right? I move on to the next one. I'm now writing equation from this one. It's just a matrix. M1, 0, 0, 0, M2, 0, 0, 0, M3. X1 dot dot, X2 dot dot, X3 dot dot, plus K1 plus K2, K2 plus K3, K3. Right, this is minus K2, minus K3. So this is what we have. So this is what we have, right? Minus K3, minus K2. Then this one should be minus K2. This one is a 0. Then this one is a 0. This is minus K3. Then we multiply by displacement X1, X2, X3, and then it should be equal to 0, 0, 0. Then we are done. Are we lost on writing? We are just taking this into an equation. Are we there, all of us? That's why I thought we need to be here physical, so that we discuss rather than talking on WhatsApp. together, right? If we have a Zoom, we have Sheila, are you following? Are we lost somewhere? I can repeat. You are there. Are we there, all of us? Can I move now? Okay. So there we are. I'm now rubbing this side. The question is, how do we get this? The one that we use for design. Was our idea is from today or from next week, you should now be able to come up. Controllers, we are very good. We have computer scientists here. They can help us in terms of design and programming. You can use Python, can use whatever kind of software so that we make all of those things. So I'm rubbing this one. Right, I'm done. Can I move on? Anyone lost? Right, Kapil, what is the value of x in terms of Naberian logarithms? You remember? Have you heard about x is cos a e I omega? You remember that?
It's the first time hearing it.
Are you sure? But in maths you should have done it. X is cos to this. You know this? Or cos theta plus I sine theta. You guys who did engineering, are you seeing this first time? Diagram nothing? Am I lying? Yes, Linda, you've seen this? Yes, that's x. X is sinusoidal, it changes. It can actually be on the cosine or on the sine. This one is basically means it's an imaginary value. So this is equivalent to this. This is where we get this, and obviously we now have our omega. So whenever we have x movement, we already have some natural frequency. Are we getting that? Omega is natural frequency. The omega that we always use is equals to 2 pi f. Is actually found in x. You remember? You remember, guys? Are we lost? You guys who did physics. I think this is your food. You were eating these things. But are we together there? So the next thing is now to substitute our x. We place it there. So that we come up with an equation, we determine natural frequency. You get it? So we take our x, we put it here, but this one is x dot dot, so we differentiate this twice. Do you know that I squared is equals minus 1 in the complex numbers? You remember? So it comes here. So this is the value of x. X dot dot. So we can come here and we substitute it here. We place it there. So our equation, we are going to say m1, m2, m3. We make them uniform so that our equation is able to be solved in a better way. Otherwise it will remain very much complex. So we say m1 is equals to m2 is equals to m3 is equals to m. Because we assume it's going to be the same. It's going to differ only on the frequency, right? Then instead of writing this, we are now going to write minus omega n. N is basically means varies, either 1 or 2 or 3. We are not going to write like this. Then we write like this. Then we say a e to the I omega t plus K1 and K2 and K3, we assume they are the same. Then we also factor out K here. We are going to remain with a 2 here, minus 1 here, 0, minus 1, 2, minus 1, 0, minus 1, 1. Then we are going to have this one, A, E, I to the omega t. This should be equal to 0. We cancel this. Are we there? Are we lost? Anyone lost that? Sheila, are you there? So we just factor out AEI to the omega square t. Then if we factor it out here, we divided both sides, both there is a 0 there, it goes. So we are only left with omega minus omega n, this one, right? But this one is squared, this one. Are we there? These are the Da Vinci robots that are used in surgery. They use this kind of equation, right? For you to determine their power. You use this equation. They all obey these laws, right? Is there anyone lost? We need to quickly finish. There's someone from where? There's the one from where did he come? He came. You are in Harare? Ah, okay. So that's fine. Those from where, I think they are quiet, but they need to go back. They are still simulating the robot. Okay, so this is what we have. So from this one, we are now going to have our final equation, and we can now add the two, and we call this equation a characteristic matrix. We write it like this, 2k. You can see that this one and this you can now add together. Are you seeing? These now are now monkeys and monkeys. Monkey and monkey, you can now add. Are you seeing? Because that time they were not being able to add, because this one, they are now one thing. This side, you can now add this and this. Are you getting me? You can now add this and that, because this one has been removed. So they are now in the same factor. So we take this one, 2k minus omega n, m minus k, 0. Then we have minus k. Then we have 2k minus omega n squared m, right? Minus k, then 0 minus k, then k minus m omega n squared. Are we together? We are just saying is adding this and this, this and this, this and this. These are matrices. You add this side with this and this and that. This one is not a problem, right? Everyone here has done some matrices, right? Are we together, guys? Are you happy, Bokan?
Yeah.
Ah, good. So can I simply say you are here? We now want to determine frequency. This one is called H. It's called the Hamilton equation, or this one. This one is the final equation that we use now to determine our natural frequency, right? So we are there. So you can see that with just a basic equation like that curve, you can determine its mode shape as well as its frequency without knowing some parameters, right? So are we together? So we now do determinants. You have done determinants, everyone. The most important thing and here, happy thing for me is you have all done determinants and matrices, right? So if we do this one, we set HI, determinant should be equal to 0. We set all this to 0. What does that mean? We take that equation, we now say this, we take plus, we put negative, we put plus. You remember that? The rule in matrices. This plus, this minus, this plus. You remember? Are you lost? So it starts with a plus, we go to minus, we go to plus, this becomes a minus, this becomes a plus, this becomes a minus, but we only take the upper part to simplify things. Sheila, are you following? Are you following? Dr. Node, are you following? Okay, so we are now there. Then the next thing is AD less BC. You do this, remember? You take this AD less BC. Remember? Can we do that? The issue about robotics is about calculations. But I'm going to reduce the calculations. After this, I'll do one for DH and I'm done. So that you always laugh me, eh? No one will laugh me after these things. And that professor is bad. Okay. Are you still liking me? So this is what we have. So can we simplify? You take this one, AD less BC. That's your equation. Minus AD less BC. Remember? Can you still remember this matrix? Are you sure? You forgot, but you did them in part 1, part 2, I think. Okay, so the first one is you take this, you multiply this and this minus this and that. Are we there? Then the second one minus k becomes a plus k. Then you this minus this. Are we together? Then plus 0, then all this goes because you are multiplying by 0. Right? So that one is done. So once you are done with that one, you are going to remain with your final equation like this.
Prof, can I ask why you were using the determinant?
Is to determine, you know, when we are doing determinant, is to find the unknown variables that are actually there. So we set AD, you know the basic purpose of a determinant. You know what is the purpose? What is the purpose of a determinant in the universes? What is the purpose? Guys, who did physics? Why do we do determinant? Yes. There will be quite many. Then you set something. We set this to 0 so that we are able to get this. So it's like a modulus of that. You get it, right? So we do that. So this one is that. So you get your final answer. Your final answer will be your omega n squared to the power 3. That will be your my final answer. Minus 5k over m. Right. Multiplied by omega n squared, right, plus 6k over m all squared, omega n squared minus k over m all cubed should be equal to 0. So are we there now? So this one is just coming from the equation that you expanded, and you are going to remain with this. This one we use what we call polynomial remainder theory, form 5, yeah? The lower 6 way. You've done all lower 6, yeah? Next. So this is how you get this. It's called polynomial remainder theory, Bostock and Chandler. There was a textbook called Bostock, yeah? You remember it? It has polynomials. So this is how you get it, and you get this one, and you are done. Yeah, it's not a problem. You don't need to look at that book. You just simplify this. We are done. It's not like you have to go back to bricks to learn chemistry, and now those things will just come on there. Then from there, with the polynomial, you are going to get omega 1 squared. Omega 1 squared is close to 0.1981 k over m. This is the first value of the frequency for mode shape 1. Omega 2 squared is equals to 1.5, because we don't use quadratic equation because we have 3 terms. So we use polynomial remainder theory. Right? Omega 3 squared is equals to 3.247, the value of k over m. So this is how you get, we are just simplifying this equation using polynomials to get the values of omega 1 squared, 2 and 3. Then we are done. We already have our natural frequency for system 1 and the system. So for the mode shape, we are now saying we now have our equation and we want to find the mode shape. Is you need to determine whether the robot has moved to what extent. Imagine you design your robot, then after 2 years, you want to see how it is moving up and down in terms of damping, how is it losing itself. So you measure it using mode shapes. Then from there, right? So I'm sure we are done. Then from there, we still have our basic equation, the one that we have 2k minus omega squared. You remember that one? Then from there, we now come and place for 1. Manashi, you still remember the equation? 2k minus omega squared m. Then we substitute the value for omega squared. You are going to see that all the m's will cancel, because it will remain like 2k minus 0.1981k, because there is another m and we multiply that. It's k over m multiplied by the m that is in that equation. Then this goes and you subtract. You get it now. Minus k 0, then from there minus k, then you have 2k minus 0.1981k, then the other one is minus k, then the other one is 0, then this is minus k, then this one is a k. Then from there, this is what you have. And you have then the difference between this. Someone can tell me what is difference with this one and those first equations. Those first equations were like small letter x, this one are big letter x. we call these ones now the amplitudes, right? We are now determining the mode shape of something. So if you subtract this one, you get 1.802, right? Minus 1, then we get a 0, then we have minus 1, then we also have 1.802, then next is minus 1, then next is 0, then next is minus 1, 0.802, then we factor out k. The k will go because we just factor it here. Once we factor it, it goes because there is a 0 there, then it's actually gone. Then we have our x1, our x2. So we now want to get this, that what we call the mode shape, the values that we have from the magnitude. So the first thing is you put this one is equals to 1. You factor or you set this is 1. Once this is 1, you calculate x2 and x3. Then you know the mode shape for 1 is 1.802. Then the other one is 2.247. So you are done with the natural frequency 1 for mode shape 1. Then the other one for 2, you do the same. Then for 3, you do the same. You are done. So the frequency that you get is the one that you come with and place it in this one. Then the torque of the system is force multiplied by distance, which is neutral meters, multiplied by the omega, you have your power. So if you want to get maximum power, normally in robotics we have 3 types of power. We focus much on the pneumatics, focus also on the electrical and the hydraulic. Yes. Mode shape 1, you set, you can't use Cramer's rule. You remember Cramer's rule in maths, but you can't use it there because you will not find this unknown. So you set this to 1 because your robot always, when you are setting it, the damping factor should be 1. It should not, because when a car is bought and the springs are new, it should not that's almost the same thing that happens to robots. So it should actually get 1. So you set this 1, then you determine this. So you always see that this is always 1. Then you get the value for this and this. You set this 1, then you find the values because this one is actually equal to 0. So you say this by 1, this by this by this equals to value 1. This by this, 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 you get that value. Remember? Yes?
So can we calculate damping ratio from there?
Yes, you can actually get damping ratio. Damping ratio, you remember the equations, right? WD is close to, but I don't want to give you that question. Things will be too many. But you can actually calculate the damping ratio. It's called the torque. Right? Right? You remember this? Omega n squared is equals to k over m. You remember? That's this basic equation for natural systems. So if you get the square root, omega n is equals to the square root of k over m, where k is for that spring stiffness and m is for the mass. Right? So I'm sure we are done. I will end there.
Prof,
yes.
What do you call that method of deriving the one?
This one. The one for setting is Cramer's rule, but we set this one so that there are not too many unknown factors. So thank you. You can go and finish this up. Then I think I'm done with this part. Anyone with a question? I don't think someone will fail in the exam. Right? Can I move on to the second part? Right? Now we are done. Now, can I now move on to the robots that we expect to see?
Prof,
yes?
when we're given such a question, are they numbers or do we just derive? When we're given such a question, like in the real world, like the M1, M2, does it come with proper masses and spring?
No, they will not be masses. It will be like that. Base count. Because what you are supposed to do is to, because you won't be able to measure like the actual mass for that. Because if you can come to your car today, you can see that maybe the mass is this today. But tomorrow is changing because maybe you have put a toolbox at the end. So at the end of the day, that mass will change. You remember? So when we do robotics, we do these variables, we solve it using this method. They're roughly expected. Right? So are we there now?
So what did we calculate here, Prof?
Yeah?
What did we calculate here? These final figures that we came up
This is mode shape. It's called the mode shape of, if you ask me, determine the frequency and the mode shape 25 marks. So you do this one. So if you go for the second one, you are now substituting the value for omega squared into 1.555. The first one, we use this one. The second one, so there are always 3 mode shapes because it has 3 degrees of freedom. Are we there? Okay. Right? Are we together? Can I move? Are we together with this one? Can you go back and learn on this one on your own? Is it difficult? Bokan, do you think it is difficult? You can go and redo it, right? Go and redo it, master it. So that you won't have some confusion in the exam, right? Thank you. This one I'm done. I'm going to the next one. I think I'll do only the next one and I'll be done for today so that I don't confuse you. Right? We are now going to a robot. So this was a system that we used to determine for robots. But for now, I'm now going to draw a robot. I'm sure we have talked about the revolute as well as the prismatic joints. Sheila, can you explain to me what is a revolute joint? That's like rotating, right? That's a revolute. Then a prismatic is something that is in a straight line, right? Right. So I'm now drawing a robot. So this is our first robot, and so this one in engineering is basically means it's a fixed point, right? This one is fixed point. Then from there I go up. Then this is a revolute joint, right? This is our robot. Then our robot is going this way. Then our robot is going this way. So this is what we call link 1. Then this one is what we call link 2, right? So we have link 1, link 2, link 3, right? This is our base. This is our link 1. This is our angle theta 1. This is our angle theta 2. So our angle theta 2 can actually rotate in this one. This is our angle theta 3. Are we there? Are we there, guys? Are we lost? If I just give you a robot like this, are you able to label like this? This is link 1, this is link 2, this is link 3. This is theta 1, this is theta 2, this is theta 3. So this robot is a 3P robot, right? Because it has got 3 R robot, right? It has some revolute joints. It's actually moving, right? Here is turning, here is turning, here is turning, right? So we have 3 angles, right? So once we have all these things, we can safely say, so here we have the final angle that we want our end effector to pick. Maybe it's a robot for picking apples, or if it's a robot for picking things in a stationery shop. So this one is controlled by this, and that for it to pick. So this is the final angle that this thing is moving. This is what we want. We don't want this, we don't want this, we don't want. But at the end of the day, we have to calculate all this for us to get this angle phi. Right? So the total angle phi is equals to theta 1 plus theta 2 plus theta 3. That's always the case. Phi is always obtained by theta 1 plus theta 2 plus theta 3. Are we there? Right? Then the next thing, we now want to determine the value for x. Remember in that equation that we did for trucks of train that was moving was just x. But our x, we can actually get it from this derivation, right? So we can get our x here by solving. You remember how to do vectors, right? We have here. So we want to get x is always here. Y is always. So do you know how to calculate this x for this robot? Remember we were saying M1, X1, but our X was not defined. So we can now define our X here. So X is equals to L1 cos theta 1, this one. We put it here. Resolve the components in the X component, right? Plus L2 cos, or we can actually say cos is C12. Remember, what do you mean by C12? Or this one I can just say C1. You remember matrices when we do angles? Remember? Let me write it first. Cos theta 1. Cos theta 1 plus theta 2 plus L3 cos phi. Right? So what we are saying is X is equals to L1 cos theta 1. This thing can move down. Plus L2 cos theta 1 plus theta 2 plus L3 cos theta 1 plus theta 2 plus theta 3, which is the same as phi. That's the value for X. Are we there? Anyone lost? We are okay. Can I move on? If someone to come and work Y. Kabir, you think you can try? We are now resolving in the Y. Y is equals to L1 sine theta 1 plus L2 sine theta 1 plus theta 2 plus L3 sine phi. It's straightforward, right? Are we happy? In our phi we have already defined. So we are fine. Are we happy now? Are you lost? You are not in a friendly manner.
No, just, my physics is fine for L1, we got theta 1 and theta 3.
It's what?
It's okay for my physics. Then the other one, that one where you're indicating like it's a mistake or kind of thing.
It's a?
Theta 2. Theta 2.
Theta 2.
Yeah.
The weight is 10.
Comes to, yeah, like when you represent it there, it doesn't like.
Okay. This one is always obtuse. This is acute. This is acute. The one at the center will move the maximum distance. Robotics, right? So you definitely need to, you don't say theta 2 is close to this, then you know you failed. Yeah? Because the robot will just be like this, it will not be labeled. It's you who labeled these things.
No. No, it's perfect.
Yes. Yeah. If you see me walking in the exam and say, please take note of what I said, that basically you are wrong. Eh? Then you say you are blessed because you are closer to way, then you have to cancel. That basically means. Remember what we said in class? Then you know, okay, I'm wrong somehow. So I'm sure we are done. So that's what we call direct kinematics. We call this kinematics. Kinematics, direct. Are we there? This is what we call direct kinematics. So we are there now, and we have solved that. Then the next thing is for us to solve inverse kinematics. Yes.
For those two questions, what will you solve?
You want to determine x. The value of x
and y.
Yes. Yeah. So we are there. So we now want to calculate the value for the inverse kinematics. So for inverse kinematics, you have your x. So you can actually say your x, you now want, it basically means maybe you are asked to calculate maybe theta 2 or theta 1. So it now needs to make something subject or formula. So the most important thing that you do is you say x minus, you start with this, x minus L3 cos phi. If you put this, it's equals to this. Are we there? This one I'm just, are you getting that? X minus this equals to this. Can you write that? Let's not panic. Then we do the same for y. Y minus L3 sine phi is equals to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Right? Are we there? Munashi, are you following? Okay. So this is what we have. So renaming this x prime is equals to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. This one. You rename x minus L3 cos phi to x prime, right? Is that so? Rename the left hand side, this equals to this. Then you also take the side, this one, y prime is equals to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Are we there? That one we have. Are we there? Right? The next thing, rename for, we group the terms in D and E. So this one is D and E. You can say this one is D, this one is E, this one is A, this one is B, this one is C, this one is D, this one is E. Right? Are we there? You can number your questions so that you follow. So, do we know this? Pythagoras. Yeah? That's the reason we are doing this. X squared plus y squared is equals to, remember that? Yes. Pythagoras. Is there anyone who forgot about Pythagoras? Just tell me. We have our x, we have our y, we have our c. Yes. So if we square that plus that, we are definitely going to get this. Is that so? Is that so? Who want to come and do it? Pokan. Are you there? Okay. So we are trying to equate this plus that, we get that one. Okay, so we have x prime, we have put it like that one, cos phi, then that one we regroup, then we have that one. So if we have x prime minus L1 theta 1 squared equals to that, plus L prime, that one is equals to that after rearranging. Okay, p cos alpha plus q sin alpha plus r is equals to z. So we have x, so I wrap this one. Right? Then from there I'm now saying x prime, we are here, minus L1 cos theta 1. This one, if you take this, you can just take this one. If we square this, we can actually square this one as well. C1, 2. So this one is the same thing as saying C12. This is the same thing as saying C1, S1, S12. We are now simplifying this so that it becomes small for multiplying purposes. We are now equating. Equating is just the same as saying it's the same, right? 1 squared is close to 1 squared, right? So that's what we are doing there. Then we do the same. So we take that one, this one, and this one. Then we equate, we add plus y prime minus L1 S1 squared is equals to L2 S12 all squared, right? So can we solve that? Then once we solve that, after rearranging, we can now rearrange it. Right? Are we there? We expand, we rearrange. We expand, we rearrange. We are going to have a very long equation. Minus 2L 1 x prime cos theta 1 plus minus 2Ly prime S1 C1 plus x prime squared plus y prime squared plus L1 squared minus L2 squared should be equal to 0 after rearranging. Then we are now going to use the basic equation P cos alpha plus Q sine alpha plus a basic equation R is equals to 0. So this is how we, so if you want to determine your theta 1, you can now determine it from that equation. If you want to determine gamma, you can also now determine it from that equation. So you can even make theta 1 subject to formula from that equation. That's the inverse part. Is you are now being asked to determine other things that are unknown. So you can quickly get all those things. Your phi 3, you have it, your reference point, you have it, all these things, the velocity analysis, then basically means you are done. Then once you simplify this, you can now get your all unknowns. And if you also have, you still remember, we have our equation x is equals to L1 C1 plus L2 C12 plus L3 cos phi. If you want to get velocity, you know how to do this? In the same way we did that way. It's x dot. If you want to get acceleration, you do double, right? So all those things are the same from what we did, and you can simplify all those things. You can get your velocity. If you are asked to get velocity of a robot, you simply derive ds.
Why did you put the alpha instead of our original theta?
This one.
Yeah.
This is a basic equation. So we are saying this one can actually change from either theta or to y, whatever. So this is the basic equation of maths, right? So that you can actually have this one as magnitude, take this one, and also this one, then this is a real value, you also add this one. So this is a basic equation from Pythagoras and all the equations for sine of angles. Then from there you can get your x dot, your velocity, you can also get your acceleration. Then from there you can get your Jacobian. You can be asked to determine Jacobian of an equation. You remember what's a Jacobian and what it is for? The physics guys. Yes. So you can be asked, can you please determine the Jacobian of this robot? So if you're asked to determine the Jacobian of the robot, you say J is equals to partial x partial theta 1 plus, okay, no, it's not plus, partial x partial theta 2 partial x partial theta 3. That's the first one. Then partial y partial theta 1 partial y partial theta 2 partial y partial theta 3. That's the other one. Then the last one, what do you think it is? The other one is, we have x, y, and the last one, x, y, and partial. We did three things today. We did x, we did y, we did phi. Remember? So partial phi, partial theta 1, partial phi, partial theta 1, 2, partial phi, partial theta 3. This is what we call the Jacobian of the equation. Determine the Jacobian of the end effector. So if the Jacobian should actually be 1, 0, 0, 1. If it is not like that, it's not a very good end effector. It should actually give you 0, 0, 0, 1, 0, 0, 0, 1, like the one that we did. You remember? So this is what we have. Then from there to me, I can safely say it was good for you today, right? I can give you some questions to go and work on, so that you keep on revising these things. I will give you some questions, or I will put them in the group. Questions, please, for today. I can safely close the lecture today. I think it's better. Eh? This one, we have already started dinner vendetta and the groups, but I'm not telling you. We are already in them. Right? So this one, there's a question coming. The masses, there's a question coming. The DH parameters, there's a question coming, right? So we are almost 3 questions inside the exam. We are left with 3.
Those are serious.
You just do this, yeah. Please make sure that you follow these things that I was doing. The most important thing is to know how to create the X and how to create the other unknowns form going back. That's inverse. Right? Then the Jacobian. Normally there's 8 marks in the exam. So you have to master these things so that you smile after the exam. Right?
Well, I can claim the last one. That's not okay.
The Jacobian always is like this. It's always partial the first number over the change in the variable. The second one over the change in the variable. The variable is the same, it doesn't change. Are you seeing that?
Yes.
Theta 1, theta 2, theta 3. So it doesn't change.
So
But
we start with the Jacobians.
yeah, but you need to first get your x. If you differentiate like you have your x, the one that we have, L1 cos theta 1. So you are differentiating this with respect to theta 1, right? So everywhere where there is a theta 1, you differentiate. So that basically this one and this one also has a theta 1. Remember? This one. Phi is theta 1, you remember?
Yes.
When you differentiate, so you are done. Questions, please? More questions? No more questions?
So, Prof,
Yes.
what was this that we did that we came up to get the phi value? So after we come up with the value for phi, do we then bring the Jacobian in? Or
Yes, the phi value is actually
the last part?
the last part. Then you mean here,
Yeah.
when we determine the Jacobian, is we want to see if our any factor is going to rotate in whatever we want. It should be 1, 0, 0, 0, 1, 0, 0, 0, 1. If it doesn't fall into that, you have made a mistake. Or in your design, you have to change. If you are designing something at work or you are designing a robot and the end effector does not have this, we call it what? What do we call it? 1001? Identity. Yes, it is not, if it's not an identity, the robot is not going to work well. You get it? So all those things that we did in maths, they are now being useful here. Because we are now saying if they don't work that way, that means we are in trouble. The robot will not work well. Right? Can I safely say we are done? Can I go to DH parameter again today? Or you want to relax? Let me see. The DH parameter is more into, let me go there. Anyone who is lost or who is confused, DH is a bit confusing than these ones, but you are almost there. I think the DH I'll first send in the notes, then you read through. Then if you have questions, you let me know. So you have first submitted the first assignment, right? All of you submitted, right? I'm marking them. Then we are done. We are writing a test on Thursday. We say Thursday, right? Wednesday. Did you say Thursday? Wednesday.
You say Thursday.
Thursday. Okay, so we are meeting on Thursday or Sunday. What is the best day for you? We meet Sunday. Okay, which is better actually? You come Sunday. So Sunday we write tests. So we are writing the mass thing as well as this one. That's our test for next week. We have the mass, we have the Jacobians, we have this thing. Whatever we did today is what is coming in test.
So basically we'll be dealing with the x-axis,
yeah,
the y-axis, that kind of thing.
and everything with that. Then we see if you pass or fail.
I think we should pass.
Yeah. So I know I'm left with one big thing, DH. Yeah, the DH is something that you are also going to apply it in your projects for robotics. I would love if each one of you does something related to robots because of mechatronics, mostly into robotics. So it will be good for you so that even someone asks you, what did you do in mechatronics? So what was your robot about? They assume you know a robot. They say, I never did a robot. I don't know what is a DH parameter. I don't know what is a transmissibility. I don't know what's a repeatability. Then that's a problem. They'll see me say, I'm sorry, it's okay, we'll call you next week. Then you didn't get a job, yeah? Last year, I taught guys quite good things last year. The guys who graduated this year. I think I taught them these things and they thought these were funnies. But they mastered these things. They all applied to Ireland in UK. They all, I think half the class got a job in Ireland. Yeah, when I went to UK in July, I went with about 3 of them in the same plane. They say you helped us. Our interview was mostly on DH parameters. So these things are practical. So some will think these are theoretical things. These are very practical, and a robot will not work if you don't identify these patterns. People will think you don't know. So most of the guys are in UK now, and they love me a lot because I taught them very difficult things that all the Europeans were failing to do, and they did it. They got the job. Most of them, one of them is an automation engineer, the other one is a systems engineer. They are doing these things. Yeah. So these things are right. I also give you one of the books that I wrote, which was based on. Do you all know SolidWorks? It's another thing that I have to teach you. Have you done SolidWorks, the guys from Megatronics?
Yes.
You know it?
Yes.
When can you do SolidWorks? You demonstrate to the class. Do you still remember it?
Yeah.
Good. So can you draw a simple robot? Then you analyze the stresses. Then you analyze the bonuses. You know how to do those. Yeah. It's me who taught you finite.
Yes.
Good. I taught these guys a cut finite element analysis. So finite element analysis, we are identifying smaller things that are within the robot. What can make it fail? So you are going to draw a simple robot. So please, what you can do is we identify one robot. When you identify it, you demonstrate it to the class next week after the test, so that they understand SolidWorks. Can you go and install SolidWorks? Then after his lecture, we are also going to practice it. That would be very good, right? Most of the guys. Linda, did I teach you final test cut? No, I was already left. So we have to master those things. Finite element and robotics is one course. So you draw one robot, you demonstrate to the whole class. How do you do it? How do you fix points? How do you... So once we play around with softwares, we are good to go. You get me? So he's going to do it, then I'm going to give you one assignment to do SolidWorks. Yeah, because if we do those things, at least we are now talking.
Yes.
Rather than making simple things for people to pass. But you have to apply these things, and even your projects, you will do them easy. Right? Then what are you going to demonstrate to us from computer science for controllers? I think it would be nice, Kapil, Mike and him, you demonstrate to the class. When you talk about controllers, I will leave everything to you guys, because you've done a lot of processors and yeah. Then you demonstrate one, you can just do one software, one either Java or Python. I think Python is better, so that they understand as well. Then once we are done with that, I know we are done. So next week we do SolidWorks, then the other Sunday or the other day that we meet, we do controllers. So when can we meet next? Can we meet, next we meet physically, then Tuesday we can meet on a Zoom. I'm going to talk about sensors, right? I think I'll do sensors, and Thursday I'll do actuators. The things for robotics are just too much. I'll just select a bit so that we master. Then DH parameters, I'll send them in notes, I'll send them today. How do you fix points? So it's just if you fix 1 point a robot. So DH parameters, you see they are the same with what you were doing with X, Y, and 5. It's just the same. The answer will be the same, actually. So if you don't know DH, you do this one. Yeah, so DH is about being consistent. If you are focusing on the negative side, you always use this one. If you focus on the anti-clockwise or clockwise, you take the robot in that direction. That's the same thing. So it's straightforward. So I think it's done. You do SolidWorks next week. You guys, we have to agree what you need to present to the class in terms of processors.
Probably microcontrollers.
Yes.
Arduinos.
Yes, you can even bring one, then you demonstrate to them. Because the good thing is we have computer scientists here, so they can help us. Because the brain of the robot works with the program that these guys do. So if we have a class with engineers and computer scientists, it's a very good class because they demonstrate to us. So they will show us an Arduino, they will show us some sensors, they will show us some all the connectors and all that kind of things. You just demonstrate it.
We can do maybe a quick one. We'll have a temperature sensor.
Yeah.
A servo motor that opens up.
Yes, servo motor is actually the actuator now. So we'll be holding and pointing to those things. So very soon we'll be making robots that can run and whatever. Yeah. So those things are easy and you have to master. Last time I used to teach students who were doing some high school quiz on robotics in Zimbabwe. So we were doing with Prince Edward, Pamshana and other schools. They were programming some simple robots, and when we went to United States, Atlanta, we were competing with the Japanese, 9 years old. So when we arrived, we were having Form 6 students competing with the 9 years old, 6 years old Chinese. And I said, are these competing with us? They were actually struggling to talk. We are competing with you in 6 years. I said, are you sure? Then the Chinese said, yes, this one's going to program a robot. I stopped. 9 years Japanese. So we said, well, can you come up with a robot that can quickly identify where water is? Then they were hiding some water somewhere. Then you are making things, you are putting all things. Very soon you hear the Japanese already arrived. Then our guys are saying, okay, where's that? But they are the oldest. So I think those things should actually. It's said, yeah. So we have to master. So now that we are being masters in robotics, you should by far knowing those things, right? It is going to be very good for us. So you do something next week. I don't know which. If you can also do next week. so that we quickly move. We don't have time. We're writing exams soon.
Are we doing this after the test?
Yes. I think our test will be 1 hour.
Okay, so meeting same time 12.
We can meet at 10 here. You can come earlier. 10 to 1. You can say 10 to 11, that's test. Right? Then 11 to 12, solid works. 12 to 1, you do some Arduinos. It will be more practical. These guys demonstrating to us, we listening, seeing what they are doing, explaining. It will make much sense. Right? I think let's make use of them, then it will be done. So we can meet next week, but we meet Tuesday. Tuesday with Board of Exams. So maybe we can meet Wednesday for I have to explain sensors. And I also have to explain actuators before we do. When they say sensor, you already know what's a sensor. When he is now analyzing. So the forces and everything, that's the one that we were doing. That's the one that he will be doing solid works. So when he is doing, let's listen carefully, let's see exactly. So you are going to explain step by step. I used to teach these guys finite element analysis. So that's finite element analysis. It's a component of robotics whereby you are analyzing the finer particles of a material. So this is the particle. You want to find out where will this thing fail at? This one. How can this thing fail and where can it start? Remember, a crack can start very small and it can grow. That's what we call finite element analysis. So we are analyzing fewer things. That's what he's going to do, to analyze in our robot what can make it fail. So you can actually see, it will show the red, amber, green, red regions, whereby the green, we are safe, we are saying things going well, and the red, things are not going well, it's about to fail. So all those things you have to master and you have to understand. Those are my discussions for today. Anything else? Okay, I think we have done progress today, right? So go and read. Next week we talk about the test. 1 hour I think you have to do test, right? You work fast, yeah?
So on Wednesday, what time are we meeting for this week?
Wednesday, is it okay if we meet at Wednesday 10 to 11? I'll just make it 1 hour. Wherever you are. Is it okay? 10 to 11?
I think if you can record it, so that
Okay. It's okay, but try to come. It's very important. I will record. Can you say, is it a good time? That's my question. Or you want another time? Or we can say 6 to 7. After work, 6 to 7. So we say 6 to 7 now. So that's fine. So we meet Wednesday 6 to 7. That's fine.
Wednesday this week.
This week.
Okay.
It's okay?
Sunday,
Sunday we meet at 10. We also meet here. You want to come at 12? Yeah? Oh, you are a pastor, you are a church. Okay, so that's okay, we respect that. So he's a pastor, I think it's good, our class is blessed, yeah? There's a class pastor.
Was there PDF for this?
No, son. I just put it in this way. But if you okay, yes, another person? So you pray for us before we write so that we pass. Be serious on that one. So we write a test at 10. Just bring your papers to write on. I don't have papers, unfortunately. So you just bring papers to write on, as well as pen and a ruler. Then you write your test. That will be good. I'll make that test maybe 30%, I think. The assignment that you wrote is what? It's 20%. Then the assignment I'll give you an assignment for controllers and microcontrollers, 25%. The one for SolidWorks, 25%. I think it's enough. We would have learned quite a lot. Is that so? Thank you so much. Have a nice day. Makasih, Mbak. Makasih, Mbak. Yo, Pak.